Okay, in this video, we're going to see our introduction to polar coordinates. Really, it's a review, a lot of what this is. You should hopefully have looked at some notes by now already to refamiliarize yourself with some of this stuff because we're not going to spend a lot of time on the review stuff. But let's get started. Previously, we used rectangular coordinates. You graph your x and your y. You typically have a function that directly relates x and y. X is horizontal, y is vertical. Those very same ordered pairs that you graphed with their x and their y could be graphed using two different parameters. Okay. We could identify a location based off of an r and a theta. R being related to distance from the origin. Really, we should say absolute value of R is distance because R can be negative. And theta represents angle, same way we measure as in trig, counterclockwise, starting from the positive x-axis. So here we can plot some basic points. Point A, 2 comma 60 degrees. It's a bit counterintuitive, but I usually start with the angle, which is the second number in the ordered pair. I'm going to find the location of 60 degrees or pi over 3 radians. And once I have that spoke line coming out from the center, once I have it identified, I'll move 2 units away from the origin, and there I'm plotting A. You can see the graph paper looks different than rectangular coordinates. It appears to be concentric circles. Here, each circle represents points that are a 1 and then 2 and then 3 units away from the origin in any direction. And then, bigger and bigger it goes as you go further away. So 2 comma 60 lives on this second ring outside of the origin. Point B, I have a negative radian value. That's no big deal for us. Negative 7 pi over 6. I'm rotating clockwise. Past negative pi a little bit more. It's coterminal with 5 pi over 6 on that spoke. Halfway between the first and second circles, I put point B. Onwards to point C. 45 degrees is pi over 4. But now I have a negative R value. So my point goes what appears to be away from 45. Once you've identified your angle, I want you to think of that entire spoke in both directions as a number line where the origin is 0. If you move towards the actual angle direction, you've got positive R values getting bigger. But if you go the other direction, back to 0, and then beyond 0 in the negative sense, still just acts like a number line. Here's negative 3, 4, 5, 6. Here's negative 7 in the direction still of 45 degrees. Point D, we start in the direction of pi, but then negative 1, 2, 3, 4. Here's my point D. So that's the basics with plotting points. Let's move on to graphs. Graphs of some very basic polar equations. What if r equals a constant? R equals 4 would be all the points that are exactly 4 units from the origin. It will make a circle. Okay, you can see it in green here. R equals negative 6. My friends, these are the exact same locations where R would equal positive 6 because this equation does not take into account the direction at all. So I have a circle with a radius of 6 for that one. Okay. Angle equaling a constant will make a line. If I find every single point in the direction of 2 pi over 3, not just towards it, but away from it, I get both sides of a line extending infinitely in both directions. Likewise with theta equals negative pi over 4, um, it's going to point towards negative pi over 4, but also towards 3 pi over 4. All right, so those are the basics. We're going to move on to the next page. Advanced polar graphing. We create a variety of interesting curves by making functions for r in terms of theta, many of which would be really hard to talk about easily in terms of x and y. Here's an example. This would be a fairly difficult xy equation, um, but in polar it's quite elegant. R equals sine of 6 theta. Now you should have already known the picture just seeing the equation because you've studied your polar notes from last year as I directed you to, and you've familiarized yourself with rose curves and limasones, cardioids, which are a special case of limasones. You've done all of that homework already. So you look at this and you recognize, oh, sine of 6 theta, that's a 12 petal rose. Okay. Here's another example. Now, this is one you don't have any familiarity with, but it does happen to represent a fairly common algebra function, which begs the question, can we possibly convert an r and theta equation into typical xy? And of course we can. And we've got four formulas that you already know very well. Okay? It's the same formulas we used dealing with vectors and dating back to trig, basic trig. X equals r cosine theta, y equals r sine theta. If you have r and theta, you plug them in here to get your x and your y. The other two formulas are most helpful if you have xy and you're trying to get r or theta. We see another variation of Pythagorean theorem. We see our tangent formula from trig. So with these tools, let's play around with this r equation above. First thing you might do is multiply 1 minus sine theta over to the left. From there, I can distribute the r, which is favorable because it creates an r sine theta, which we know is just y. Okay. Now, I don't love the equation in its current form. We typically want to be entirely r theta or entirely xy, no halfway. I don't want a mix of y and r in an equation usually, so I have more work to do here. I can replace the r using one of the versions of Pythagorean theorem. Just don't forget about plus or minus. Okay. So now technically we're done. We have an xy equation, but it's not in a form that we necessarily recognize. So we keep playing with it. Excuse me. I'd love to square this radical, but to make that easy, I probably should move this minus y over to the other side. Here's a form where it's easier to square. And now we're getting close. Maybe FOIL out the right. Maybe solve for y somehow. Okay. It turns out this is a parabola. 2 over 1 minus sine theta is a parabola. Okay. The real purpose of this example was to get a little practice using these formulas here. Okay. We're going to move to the next page. Do some calculus. Okay. We have equations now that will be presented to you, equations for r in terms of theta, and yet the calculus we want to do still relies on x and y. For example, tangent lines to a polar curve, as you can see in the picture down here. That tangent line has a slope, and the slope, by definition, compares rate of change of y to x. Now, if your equation is r's and thetas, well, that's a problem because dr d theta might be easy to find, but it's not slope. It would be the rate of change of distance from the origin with respect to the angle you're pointed at. That's not what slope is. Okay, so we do have some extra work to do to get a dy dx, but hey, that's why we learned these equations on the previous page. x equals r cosine theta. So if you have an equation for r, just put a multiplier of cosine on it, and now it's an equation for x. Similar for y. Okay, y equals r sine theta. If you were given the formula for r, multiply a sign on it. Now it's y. That's how we do these things. So let's look at the example below. Um, Once we've done these multipliers, by the way, what I want to point out, you have x and y each written in terms of another parameter, theta. This is just parametric equations at this point. Instead of a t, you see a theta. T for time, well, sometimes parametric equations we use theta because it's an angle direction is that extra parameter. So it's pretty common in polar. We're really just doing parametrics all over again for some of these tasks. Okay. Anyhow, uh, to find the equation of this tangent line when theta equals pi over 4, your first thought might be, well, that certainly doesn't look like it's the direction of pi over 4, does it? Well, hold that thought because, my friends, you should know a trig circle by now. And when you have an equation, we should know how to plug numbers in. You could test for yourself why this picture does make sense. If I put a pi over 4 in here times 6, okay. Well, now it's sine of 3 pi over 2, which is negative, so it's a negative r value. And now it makes sense, right? In the direction of pi over 4, but with a negative r value does land us down at this tip in quadrant 3. Okay, but anyhow, we're going to find the equation of the red tangent line, point slope form. Firstly, to find a point, you need your x and your y. We just talked about this. X is equal to r times cosine, y is equal to r times sine. So we're going to take that r, put on the multipliers that we need, and then we're going to plug pi over 4 into all of that. And it's going to work out pretty nicely if you know your unit circle, but maybe test it yourself. I have very little patience at this point in the year for unit circle errors. Okay. I will not be in a good mood if I see this on an exam. So check these for yourself. Make sure you can get there. Make sure you study your circle if you need to. All right, so those are the coordinates for my point. Now I want my slope. It's a dy dx, which means dy d theta over dx d theta. This is the same formula from parametric with t. Be careful with these derivatives. It is product rule now because of these multipliers we put onto the r equation to turn them into x and y. So try it yourself and then check against my work here and then very carefully plug in pi over 4 everywhere. And if you do this correctly, it does work out very, very nice that your dy dx eventually is just -1. So we package it all together in point slope form. Y minus the y coordinate equals -1 times x minus the x coordinate that was also negative. And there's my tangent line. Okay, moving along. Yeah. Okay. Uh, Here at the top, again, the observation, polar coordinates is really just parametric for some of the tasks with theta instead of t. Yeah, for that reason, we see a certain formula now for the third time this chapter. We are integrating what looks like Pythagorean theorem with derivatives, first derivatives, instead of, actual legs of a right triangle. Okay, this is the way to find the length around a polar curve. Okay, same method to find distance traveled. Okay, so there's a little bit of a problem here with our third iteration of this formula. The problem is that oftentimes when you're asked to do arc length, you were given an equation for r in terms of theta. So while this formula here is easy to remember, it's not actually easy to use because now you have to find equations for x and y in terms of theta, same as what we did on the previous page. And then you have to differentiate both of those, which is probably going to be product rule. And only then can you plug things into this formula where now you have to integrate. So I'm going to show you a trick to make it easier. The trick is not required. There have been years where I didn't even show this formula to my class. Um, so proceed with caution at your own risk here. This formula down here is not a shortcut if you can't remember this formula. The top one is easier to remember, okay? But the alternate strategy allows us to find arc length without ever going to x or y. I can stick with just the equation for r and then dr d theta. In fact, it's the square root of r squared plus dr d theta squared, okay? If you're skeptical that these formulas could be equivalent, I do have a proof down here that I'll leave for you to look at on your own. You can see my work. You can ask me about it if you like. But it does show that these two are equivalent. Okay, so you have to make the choice. I think there's a logic to just learning the top one. It will take a little more work to get there, but it's work you have to know how to do anyway, I suppose. The bottom one, if you're feeling confident, you can go for it. The next page shows two setups separated by this horizontal line. We want to find the length if you were to travel around this limacone, okay? R equals 2 plus 3 cosine theta. Now, if I use the shortcut formula, it's quick and easy. I'm going to take my R, plug it right in, and square it. I'm going to find the derivative of R with respect to cosine, which is just, well, negative 3 times sine. Plug that right in and square it. And there's your setup. And it's most likely a calculator problem. And then you go to your calculator. If I were going to set this up the other way, first I'd have to show some work of, okay, here's an equation for x in terms of theta. I'm just taking r times cosine. Y is r times sine. Then I'm differentiating both of those with product rule, and they're getting a bit more complicated than the original formulas, and then I would have to plug them in, which I guess I could take a shortcut in the notation if I've already written these out earlier, but it's just a little bit more work. Try it both ways. See that you get the same answer both ways. Okay. That's the end of this video. There will be a part two that gets into the fun stuff where we start finding area within curves like this. Okay. If you have any questions, feel free to email me. Thank you for watching. Goodbye.